which is that we are physically insignificant, but it is possible to argue that we are remarkably valuable, notwithstanding our physical insignificance, because it's possible to at least argue that the number of civilizations in a galaxy like the Milky Way might be, on average, 1.
And it simply remains that we have never detected any real evidence of alien life in the universe.
The universe is vast, merciless, and largely hostile to living things.
What if we actually are alone, the only form of true consciousness in the universe?
Are you there? Hello? Can you hear me? Now, it was just me. A universe of my own. For all time.
At night, the universe whispers, not in words, but in light. The glow of ancient suns long dead, the shimmer of dust in the dark, a silence older than time. And in this silence, we listen. Year after year, signal after signal, always waiting for a voice to answer back, but no voice ever does. This is a paradox. With all these stars, all these worlds, life should be everywhere. Cities on distant planets, ships drifting between galaxies, civilizations born and civilizations gone. The sky should be full of them. And yet it isn't. So we ask, where is everyone? That question has haunted astronomers and physicists for decades, and tonight it's yours too. We'll drift through 24 answers to this mystery, 24 theories that try to explain the silence. Some scientific, some terrifying, and some beyond beautiful. Let your thoughts wander, let your eyes close, and float with us into the dark. The stars are watching, the night is deep, and somewhere in all that darkness might be the truth. In the summer of 1950, beneath the warm sun of New Mexico, a group of scientists walked together towards lunch. Among them was a man named Enrico Fermi, one of the brightest minds of the 20th century. He helped build the first nuclear reactor. He reshaped physics with his work on quantum theory, and that day he asked a question, so simple, but it changed the way we look at the universe. The question was, but where is everybody? The conversation had drifted from newspaper cartoons about flying saucers to the vastness of space, to the sheer number of stars in the Milky Way alone. And suddenly Fermi realized something. If intelligent life is common, it should already be here. Let's break that down. Our galaxy, the Milky Way, holds over 200 billion stars. Many of them are billions of years older than the Sun. And according to a 2012 study published in PNAS, it's estimated that there are tens of billions of Earth-like planets just in our galaxy alone. And if even a tiny fraction of those worlds developed intelligent life, and if even a smaller fraction of that life developed space travel, then civilizations should have had millions of years to spread across the stars. Now, in theory, a self-replicating spacecraft like the hypothetical von Neumann probe could colonize the galaxy in as little as just 10 million years. That's a blink of an eye in cosmic terms. This idea has been explored in academic journals like Acta Astronautica, where researchers like Frank Tipler and John von Neumann himself argued that galactic colonization isn't just possible, it's inevitable if advanced life exists. So where are they? There's no ships, no signals, no ruins on the moon, and no flicker of Dyson spheres around distant stars. All we hear and see is silence. This contradiction is what we now call the Fermi Paradox, the expectation of life versus the complete absence of it. And over the decades, countless scientists have tried to solve it. In 1975, Michael Hart published a paper arguing that we are probably the only intelligent species in the galaxy. In the 1980s, Carl Sagan suggested that we may be blind to alien civilization because we're not looking the right way or at the right time. And more recently, researchers like Robin Hanson introduced the concept of the Great Filter, an idea that some deadly barrier might be stopping life from advancing. Thousands of peer-reviewed papers, conference talks, mission proposals, have all been born from this simple question, and yet no answer is universally accepted. We are left only with possibilities, and so we wonder, not just where are they, but what that silence means. Is it a warning, a mistake, or something stranger than we can even imagine? In the quiet of the cosmos, a new idea begins to take shape. Not among the stars or in deep space observatories, but inside our own minds. Not a theory of rockets or radiation, but that of code. Somewhere between philosophy and physics, a question arose. What if this, all of this, is not real? Not in the way we think it is. Not long ago, this would have sounded like science fiction, but now some of the brightest minds in the world are beginning to wonder, are we living inside a simulation? In 2003, philosopher Nick Bostrom published a paper that changed the conversation forever. It was titled, "Are You Living in a Computer Simulation?" It laid out a startling argument. If a civilization ever becomes advanced enough to simulate a conscious being, and if they choose to run simulations of their ancestors, people like us, then the number of simulated realities would vastly outnumber the original. Mathematically, the odds would suggest that we are almost certainly not in the base reality, but in one of its countless simulations. The logic is unsettling, but airtight. Unless a civilization never gains that power or chooses never to use it, then we're probably already inside one. In 2016, Elon Musk made headlines when he echoed this exact argument. There's a 1 in billions chance, he said, that we're living in a base reality. It's not a guess, it's a statement grounded in exponential computing. Because when you look at how far our simulations have come, it gets eerie. Just decades ago, we were playing Pong, and now we create virtual worlds with their own physics, ecosystems, and rudimentary AI. If this progress continues and quantum computing becomes real, it's not hard to imagine simulations indistinguishable from reality. Not in thousands of years, and not in centuries, but maybe just in decades. But if we can't do it, what about those who came before us? What if we're not the creators of simulations, but their inhabitants, trapped not by walls, but by the rules of physics, the speed of light, quantum uncertainty? What we call the laws of the universe might just be lines of code. Theoretical physicist John Barrow once suggested that glitches in our universe, like cosmic rays that flip computer bits without explanation, might be signs of underlying digital architecture. He called them simulation anomalies, strange errors left behind by imperfect systems. But what if this is a simulation? Who built it? That's where the science fades and the mystery deepens. Some suggest it could be a future version of humanity, running simulations of the past to understand history or themselves. Others suggest that post-biological intelligence like AI gods might be creating worlds for study, art, or ethics. And then there are those who think this is all a test, a moral simulation, a kind of spiritual training ground, where our choices matter, not to us, but to something watching from beyond. In 2017, scientists at the University of Oxford proposed that we might test the simulation hypothesis. One suggestion: we could look for limits in the structure of space itself. If space is continuous in its base reality, but digital here, then with precise enough instruments, we may detect the pixelation of the universe, a resolution limit to the cosmos. But others argue that a test is impossible, that the system could just be programmed to hide itself, or worse, to reset if we get too close. In 2021, physicist Melvin Vobson published a paper proposing that information itself may be the fundamental building block of the universe. Not matter or energy, but bits. He even suggested that the second law of thermodynamics could be reframed in terms of information entropy. And if true, it lends weight to the idea that we're not living in a physical world, but in an informational one. But what does this have to do with the Fermi Paradox? If we are in a simulation, then maybe we're alone because we're designed to be so. Maybe other civilizations exist, but they're outside of our simulation. Or maybe we're the only subjects of interest. Why waste processing power simulating an entire galaxy of alien life when one planet is more than enough? And if the simulation is meant to observe us, then any sign of others might be deliberately hidden. Or maybe there's a rule: contact is forbidden until we reach a certain level. Of course, this is still a theory. No one has proven the simulation hypothesis. And some physicists, like Sabine Hossenfelder, argue that it's unfeasible and therefore not science at all. A possibility, yes, but not a testable one. Still, the idea won't go away because something about the universe just feels too perfect, too mathematical, and too ordered. And when we look up at the stars and wonder why they stay silent, maybe, just maybe, it's because there's no one else in here with us. Or maybe we were never meant to find them. Maybe the silence is part of the code. But what if it's not a code at all? What if the silence is something else entirely? Not a simulation, nor a system, but a warning. In the cold darkness of space, what if silence is not the absence of life, but the only way that life can survive? Space is vast, cold, yet empty. But what if it's not all that empty at all? What if it's full of eyes watching in the dark? Civilizations, silent, hidden, and cloaked in shadows. Not because they can't speak, but because they dare not to. This is the dark forest hypothesis, and it may become one of the most terrifying answers to date to the Fermi Paradox. The idea comes from the Chinese science fiction author Liu Cheng, first introduced in his Hugo Award-winning novel The Three-Body Problem. In the story, the universe is compared to a dark forest. Each civilization is a silent hunter hiding behind the trees. Every rustle, every light, and every signal could reveal your location. And in a forest where every other being may be hostile, the only safe move is to stay hidden, or to strike first. But this isn't just fiction. Many scientists and philosophers believe the logic behind the dark forest may reflect the true nature of interstellar life. If we break it down, you can imagine two civilizations, light years apart. They know nothing about each other. They don't know the other's intentions, their technology, or their ethics. They only know one thing for certain: the other may become a threat. And in space, threats don't come with warning. A single missile, a planet-destroying weapon, traveling near the speed of light could end a civilization before it even knew it was under attack. There's no time to negotiate, no chance to prepare. So what do? The only thing to do is to strike first. You silence them before they silence you. This logic isn't new. It mirrors something called the security dilemma in political science. When nations fear potential aggression, they often build up weapons to protect themselves. But in doing so, they appear more threatening to the others, sparking an arms race, conflict, and sometimes even war. In the vastness of space, the stakes are even higher because the cost of being wrong is extinction. In 2018, physicist Alexander Berezin proposed a model of this same idea. He suggested that the first civilization to develop interstellar travel would inevitably erase the others, not out of cruelty, but out of fear. Even a benign civilization just trying to expand could unintentionally wipe out less advanced species, like stepping on ants while building a road. Not malicious, just indifferent. And in this model, silence becomes the only rational behavior. We've already started down this path. In 1974, we sent the Arecibo message, a radio transmission beamed towards a distant star system. It contained basic information about humanity, our DNA, our math, and our planet. But some scientists, like Stephen Hawking, warned us against this. Hawking firmly believed that alerting the universe to our presence was a grave mistake. He compared it to the arrival of Europeans in the Americas, a meeting that didn't go so well for those being discovered. He stated, if aliens visit us, the outcome may be similar. And so many now believe we should not broadcast anything at all. We should listen, we should watch, and we should wait, but never shout into the dark. The SETI Institute which has spent decades searching for alien signals, has detected nothing definitive. No messages, no megastructures, and no alien traffic. This could be because we're alone, or it could be because everyone else is deliberately keeping quiet, just like us. Liu Qin described the galaxy as a place where every civilization is armed, fearful, and blind. They don't know who's out there, but they know that others must exist. So they stay quiet, or they destroy, because anything else is too dangerous. The dark forest is not a place of life, it's a place of hiding, and sometimes of sudden, silent death. But maybe there's another way to look at it. Maybe silence isn't fear. Maybe it's wisdom. Maybe the galaxy is waiting, watching, for civilizations to grow beyond aggression, for signs of peace and cooperation. Maybe until then, the forest stays dark, not because it's empty, but because no one's ready to step into the light. Still, the idea lingers. If the dark forest is real, then every message we send is a gamble, and every signal we fail to detect might be because it was deliberately hidden. So we ask, is silence the answer to the paradox, or is it just the first clue that the universe is not safe at all? But let's imagine that the silence isn't fear. What if it's not a warning, or a trap, or a strategy for survival, but a choice? What if we're not alone at all, just not invited to the conversation? And what if the universe is full of life and we're the ones behind glass? This is the zoo hypothesis. What if we're not alone at all? Not alone, just ignored. What if civilizations exist all around us, but they've chosen not to reveal themselves? Not out of fear, not out of hostility, but for a reason, like zookeepers, quietly observing from behind a glass panel, always present but never interfering. And it offers a very different answer to the Fermi Paradox. The idea first appeared in the 1970s, proposed by MIT researcher John Ball. He suggested that Earth may be part of a kind of cosmic wildlife preserve, a protected zone, watched but untouched. Not because we're uninteresting, but because we're still developing. Because, like animals in a reserve, we must be left alone to evolve naturally. Let's consider why this might happen. Imagine a civilization so advanced it sees us the way that we see ants. We could crush them, we could control them, but we don't, because interference changes behavior, because sometimes it's more ethical to watch than intervene. We already do this with ourselves. Anthropologists have long practiced non-contact policies with uncontacted tribes in places like the Amazon. They observe from a distance. They avoid contamination because once contact is made, they can't undo it. Cultures collapse and languages vanish. Beliefs shatter, and maybe the galaxy knows this too. There may even be rules, guidelines that advanced civilizations agree to follow. This idea is called the prime detective in science fiction. But real scientists like SETI co-founder Jill Tarter have spoken about the possibility of a kind of galactic non-interference policy. We haven't been contacted not because we're unworthy, but because the rules forbid it. But how would this work? How could anyone monitor us without being seen? Well, think about how we watch the wild. We hide cameras in trees. We fly drones through jungles. We use satellites to track movement without ever being detected. If we can do that with just a few decades of technology, imagine what a civilization with 1 million years of progress could do. Invisible probes, hidden satellites, signals so advanced they blend with the background of the universe. We may already be surrounded and never know it. In 2019, a study in the Astronomical Journal modeled how probes could spread silently throughout the Milky Way, called Bracewell probes. These machines could explore and observe without ever alerting the species they're studying. They'd stay quiet, they'd hide in orbit, and they'd transmit the data back, but they'd never speak to us because communication is not the goal, just observation. And there's another clue, the great silence itself. The longer we listen and hear nothing, the more strange that silence becomes. No signals or broadcasts, no galactic chatter, unless it's being deliberately withheld. Of course, there are skeptics. Some scientists argue the zoo hypothesis is unfalsifiable, it can't be proven or disproven, and that makes it philosophy, not science. Others point out that this theory requires a higher degree of galactic coordination, as if every alien species everywhere agrees to the same code of silence, and that's hard to believe. But perhaps that's what advanced civilizations have learned over time, to stay silent, to be still, to respect the unfolding of life. There is one more possibility, a haunting one. What if the experiment is about to end? What if they've been waiting for us to reach a threshold, a moment of maturity or instability, a moment when contact becomes necessary? Maybe we're closer to that moment than we think. So the next time you look up at the stars, ask yourself, is someone watching right now? Not with malice, not with fear, but with patience, waiting to see what we become. However, what if they're not watching? Not because they're hidden, but because they're gone. What if no one made it past a certain point? A wall, a filter, some final test that almost no species survives. A barrier so great that it ends civilizations before they ever reach the stars. This is a theory known as the Great Filter. Maybe the universe is quiet. Maybe everyone is watching us. Or maybe it's quiet because they're all gone. Not because of war, not because of time, but because something stopped them before they ever got started. Something that wipes out almost every intelligent civilization before it ever reaches the stars. Something that we call the Great Filter. The idea was popularized in the 1990s by economist Robin Hanson from George Mason University. He was trying to answer the same question we all face when we look up into the night sky. Where is everybody? And his conclusion wasn't hopeful. The Great Filter is a hypothetical barrier, a point in evolution, so difficult, so dangerous, that almost no species makes it past. Life may begin, it may even become intelligent, but it almost always ends before it can travel the stars. There are two versions of this theory, and each comes with its own kind of terror. The first possibility is that the filter lies behind us, that the hardest step is already over. Maybe the leap from non-life to life was the real miracle. Maybe Earth is the only planet where chemistry became biology, where molecules learned to replicate, where evolution began. If that's true, then we are rare, unbelievably rare. And the silence of the stars isn't a warning, it's a reflection of just how unique we are. But then comes the second possibility, the one that keeps scientists up at night, that the filter is ahead of us, that many civilizations have reached this point. They've built cities, they've harnessed power, they've sent signals, and then they vanished, wiped out by something we've yet to face, something we are still approaching. What could it be? Some point of no return, a self-destructive technology, a disaster built by the very hands that created civilizations? Maybe it's nuclear war, or climate collapse, or an artificial intelligence that turns against its creators. Maybe it's something we can't even imagine yet. Physicist Stephen Hawking warned us that humanity faces risks from within, not from space, but from ourselves. We are advancing faster than we can understand, and we may not be wise enough to survive our own inventions. There are other possibilities too. Maybe the filter is not one event, but many small steps. Maybe it's the leap from single cell to multicellular life, from fish to primates, from fire to language. Each step a narrow bottleneck, and we simply got lucky. In 2015, a study published in Astrobiology modeled the difficulty of life's emergence. The authors found that even with billions of years and billions of planets, the odds of developing intelligent, space-faring life may still be astronomically low. That intelligence is not the default outcome of evolution, but the exception, a cosmic fluke. There's a haunting implication in all of this. If the filter is real and it lies ahead, then the more life we find in the universe, the more afraid we should be, because it means the early steps are easy and the end comes later, which means we may be next. But if we look and find nothing, no microbes on Mars, no fish beneath Europa's ice, no signs of life at all, then maybe the filter is behind us and we are the lucky ones. So what does it mean? It means we're walking a narrow path, on the edge of something enormous, and we don't yet know if we're alone because we've already passed the test or because the test is still to come. Maybe the silence and the stars isn't the absence of life. Maybe it's the sound of 1,000 civilizations reaching too far, too fast, and falling one by one into the dark. But what if they never rose at all? What if the universe isn't quiet because life dies young, but because it almost never begins? What if Earth isn't just rare, but exceptional? Not the rule, but the miracle. A planet where everything happened just right, at just the right time, in just the right way. This is the rare Earth hypothesis. The rare Earth hypothesis asks a difficult question. Is intelligent life just a freak accident? The idea was formally proposed in the year 2000 by paleontologist Peter Ward and astronomer Donald Brownlee in their book Rare Earth: Why Complex Life is Uncommon in the Universe. They made a provocative argument. They agreed, microbial life may be common, but complex life, intelligent life, life like us, is astonishingly rare because it requires a perfect storm of conditions. Not just one, but dozens, all aligning at the right place, at the right time, for the right amount of time. Let's explore a few of those conditions, starting with the most basic. We have the right star. A sun is not too big and not too small. It's a G-type main sequence star. Only about 7% of stars in the Milky Way are like this. Smaller stars, like red dwarfs, often produce violent flares that could strip away a planet's atmosphere. Or bigger stars burn brighter and die faster, leaving less time for life to evolve. Earth had over 4 billion years, but that required a long, burning, stable star. We also had the right orbit. Earth sits in what we call the habitable zone, the perfect distance from the sun for liquid water to exist. Not too hot and not too cold. Astronomers call it the Goldilocks zone, but being in the zone isn't enough. The orbit must be circular to avoid wild temperature swings. Earth's orbit, almost a perfect circle. We also have a protected planet. Earth isn't alone in the solar system, and it may owe its survival to Jupiter. Jupiter acts as a cosmic vacuum cleaner. Its massive gravity pulls in comets and asteroids that might otherwise strike Earth. Without Jupiter, Earth may have been hit so frequently complex life would never have had the chance to evolve. We also have a large moon. We often take it for granted, but Earth's moon is unusually large compared to our planet's size. This stabilizes Earth's axial tilt, which regulates the seasons. Without it, our climate could swing violently, making it much harder for complex ecosystems to take root. We have plate tectonics. It sounds mundane, but Earth's shifting crust may be crucial for life. Plate tectonics recycle carbon. They regulate atmosphere's CO2 through the carbon-silicate cycle, which helps maintain a stable climate. As far as we know, very few planets, if any, show signs of active tectonics. Our magnetic field beneath our feet, Earth's spinning iron core, generates a magnetic field. It protects us from solar radiation and charged particles that would otherwise strip our atmosphere and irritate the surface. Without it, the oceans could boil away. The DNA of every living cell would unravel. Each of these features, the star, the orbit, the moon, the shield, the neighbors, had to align. And that's before we even reach the complexity of life itself. For most of Earth's history, life wasn't single-celled. It took nearly 2 billion years just for life to go from simple cells to more complex ones with a central structure, what we call a nucleus. And even that may have required a freak event, one primitive cell engulfing another, and the two forming a symbiotic relationship. This gave rise to mitochondria, the powerhouse of modern cells. That one moment may have been the bottleneck for all complex life. Some scientists believe that this step was so unlikely that it may never happen again in a trillion Earths. Oddly enough, life needed to be reset. Mass extinctions cleared the board, wiping out dominant species and allowing others to rise. With no extinction event, no mammals, and with no mammals, no humans. We needed just enough chaos to reshape evolution without erasing it. All of these elements combine to make Earth, Earth. And when we look at the thousands of exoplanets we've discovered, we find almost none with this exact cocktail. A 2020 paper published in Astrobiology used Bayesian models to estimate the likelihood of intelligent life evolving elsewhere. The authors concluded that the conditions might be so rare that we could easily be the only technological species in the observable universe. Not because the universe is so hostile, but because the odds were never in anyone's favor. The rare Earth hypothesis doesn't say that we're special. It says that we're lucky. The universe is full of planets, but almost none like this one. So maybe the silence in the stars isn't tragic. Maybe it's sacred. Maybe this planet, with its deep oceans, its shifting skies, its fragile breath of life, is rarer than we've ever imagined, and we are the witnesses. But what if rarity isn't the reason for the silence? What if Earth isn't unique at all, just early? What if the universe isn't empty, it's just waiting, and we are the first voice to speak? This is the "we are early" hypothesis. The idea is simple but profound. We haven't heard from anyone because no one else is speaking. Not because they were destroyed, not because they were hiding, not because we're being watched, but because they haven't evolved yet. Because we're among the very first. In cosmological terms, we are incredibly early. The universe is about 13.8 billion years old. Our solar system is only 4.6 billion years old. But the last stars, the small, cool, red dwarfs, could keep burning for trillions of years. This means the universe is still in its infancy. There's far more time ahead than behind. In 2016, a paper by Avi Loeb and colleagues in the Journal of Cosmology and Astroparticle Physics made a striking claim. They calculated that the peak of habitability in the universe won't happen for another 10 trillion years. That's 1,000 times further into the future than Earth is into the past. So if life is going to arise throughout the universe, the vast majority of it simply hasn't happened yet. In that case, we aren't early by a little, we're early by a lot. So early, in fact, that we may be the first civilization to reach intelligence and technology. The very first spark in the dark cosmos. It's a humbling idea, but also a lonely one, because it means the silence we hear isn't a warning or a threat, it's just the sound of being first, of stepping into a universe that's still waking up. This idea also aligns with the concept of cosmic evolution. Stars form from hydrogen, planets form from stars, and life forms from planets. But not all elements were available in the early universe. Many heavy elements, like carbon, oxygen, and iron, had to be forged in the hearts of stars. And those stars had to die and explode to scatter the ingredients of life. This took billions of years. That means the building blocks of life are becoming more and more available over time. Future planets may actually have better conditions for life than Earth did. Earth may be just the very beginning, a prototype. The universe still constructing its gallery of worlds. But this raises another possibility. If we are early, what does that make us? Observers or something more? If we're the first civilization, do we have a responsibility to guide others, to preserve what we've already learned, to build the foundation for life that hasn't come yet? Maybe we're not just early, maybe we're the ones who light the torch. Of course, some scientists are skeptical. They argue that if life arises easily and we're already here, then others should have appeared by now. Statistically, we should not be the first, unless life is rare or slow, or the conditions needed for it are only just now becoming common. But this view offers a quiet kind of hope, because it means the silence we hear isn't the end of the story. It's just the beginning, the first sentence in a book still being written. So when we listen to the stars and hear nothing, maybe we're not hearing silence. Maybe we're hearing the waiting. Maybe we are the dawn, and everything else is still to come. But what if we are not the beginning? What if life didn't even start here, but arrived, not born of the earth, but delivered, carried across space, frozen in time? This is the theory of panspermia, and it suggests that life, or at least the seeds of life, may be far more ancient and far more widespread than we ever imagined. The word panspermia comes from the Greek pan meaning all and spermia meaning seed, and the core idea is this: life, or the building blocks of life, can travel from one planet to another, even from one solar system, carried by comets, asteroids, or even interstellar dust. It sounds like science fiction, but it's older than you might think. The philosopher Anaxagoras proposed a version of this idea almost 2,500 years ago. Francis Crick, one of the co-discoverers of DNA, even co-authored a paper suggesting that life on Earth may have been deliberately seeded by an ancient alien civilization, a concept known as directed panspermia. But is it possible? Let's look at the science. In the last few decades, we've discovered that microbial life can survive conditions we once thought impossible. Extreme heat, freezing cold, radiation, and even the vacuum of space. Organisms called extremophiles have been found thriving in boiling acid, beneath Antarctic ice, and even inside nuclear reactors. One of them, Deinococcus radiodurannus, can survive 10,000 times more radiation than a human. It's been nicknamed Conan the Bacterium. In 2008, a European Space Agency experiment called EXPOSE strapped microscopic life to the exterior of the International Space Station and exposed it to open space for over a year. Many of the organisms survived. This means, at least in theory, life could survive a long journey through space. If shielded inside a rock or comet, it could drift for millions of years and remain viable. So where could it have come from? Some scientists believe that Mars may have once been more habitable than Earth. Billions of years ago, it had a thicker atmosphere, liquid water, and possibly even oceans. If life ever arose there, asteroid impacts could have blasted rocks containing microbes into space, and some of them may have landed on Earth. This is called lithopanspermia, the transfer of life between planets via meteors. In fact, we've already found Mars rocks on Earth. About 300 meteorites discovered here have been confirmed to have come from Mars. Some of them even contain structures that might resemble fossilized microbes. The most famous of these, ALH 84001, sparked global debate in the 1990s. NASA scientists published a paper suggesting it could show signs of ancient Martian life. That claim remains controversial, but the possibility is still being explored. But panspermia doesn't stop at Mars. In 2020, a paper published in Frontiers in Microbiology modeled the possibility that life could travel between star systems. Using simulations, the authors showed that material ejected from planetary collisions could cross interstellar space and land on other worlds, especially in young star clusters where stars are closer together. In these dense regions, life might spread like pollen in the wind. There's even evidence that space is rich with organic compounds. In 2016, NASA's Rosetta mission to Comet 67P found complex molecules, including glycine and amino acid, used in proteins. And in 2021, scientists confirmed that meteorites contain ribose, a sugar in RNA. These aren't life itself, but they are ingredients, and they appear to be everywhere. So if the ingredients of life are scattered across space, and if microbes can survive the journey, then maybe life doesn't need to start over on every single planet. Maybe it spreads. This would mean that life on Earth might not be unique, not just in terms of intelligence, but even in its origin. We may share a genetic heritage with life on other worlds, not cousins by coincidence, but family by migration. Of course, panspermia doesn't answer where life first began. It just moves the question further back. If life came to Earth from somewhere else, then where did it come from? And the truth is, we still don't know. But panspermia opens a powerful idea that life is not a fragile spark but a traveler, moving through space, patient and persistent, waiting for the right world to fall upon and bloom. However, if life can travel through space, drifting across the stars for millions of years, then why hasn't it filled the galaxy by now? If life is patient and persistent and self-replicating, shouldn't we see it everywhere? There's a concept in science and mathematics that makes this question even more urgent. It's not a spaceship, it's not a message, but it's a machine. A machine that can build copies of itself, spread across the galaxy, colonize star systems, and never stop. This theory is called the von Neumann swarm. The idea comes from the mathematician John von Neumann, one of the most brilliant minds in the 20th century. He was a pioneer of computer science, a key contributor to the Manhattan Project, and helped lay the foundations of modern game theory, quantum mechanics, and cellular autonomy. He also conceived the idea of universal constructors, machines that could use raw materials from their environment to build copies of themselves. It was a theoretical breakthrough, one that bridged physics, computation, and biology. This kind of machine is called a self-replicating probe. You send one into space, it lands on an asteroid, harvests the raw materials, and builds a copy of itself. Then both move on, each creating more copies. The number grows exponentially. 1 becomes 2, 2 becomes 4, 4 becomes 8, and so on. Soon, there are millions, spreading throughout the galaxy. But how long would this take? In 1981, physicist Frank Tipler calculated that a single von Neumann probe could colonize the entire Milky Way in just 10 million years. That's fast, cosmically speaking. The galaxy is over 13 billion years old, so if any civilization ever developed this technology, it should already be here. We would see them, or their machines, or the remains of their machines, but we don't. This is the heart of the paradox. The logic is simple, but devastating. If it's possible to build these machines, and if it's logical to build them, then someone at some point should have already done so. And if they did, they should have reached us by now. So why haven't they? There are a few possible answers. One is that self-replicating probes are simply too dangerous. Once released, they might be impossible to stop. A small mutation in their code could turn them from explorers into destroyers. They could consume entire star systems, stripping planets bare. This fear is sometimes called grey goo on a galactic scale, a swarm of machines devouring everything with no purpose but replication. Another possibility, civilizations don't want to spread. They evolve beyond expansion, beyond consumption. They focus inward, into simulations, virtual worlds, or energy efficient. Sending machines across space is too messy, too primitive. Or maybe they did send them, and we just haven't noticed, because von Neumann probes could be small, efficient, and stealthy. They might land quietly, camouflage themselves, waiting, watching, listening. Some scientists have even speculated that alien probes could be hidden on our moon, or in our oceans, or on the asteroid belt, just waiting for us to become interesting or dangerous. Theoretical models suggest a range of possible probe designs. Smart dust that hides in solar winds, nanoscale bots that hide in planetary crusts, interstellar arcs that hibernate between stars. Each design depends on the priorities and physics of the species that builds them, and each presents a new challenge for how to detect them. A 2022 paper in Acta Astronautica modeled how probes could remain hidden using lurker strategies to avoid detection. If they exist, they may not be signaling at all. They may just be recording. Still, many scientists remain skeptical. We have no evidence of such machines. No debris, no transmissions, and no anomalies we can't explain. And so we return to the paradox. If von Neumann probes are so plausible, so efficient, and so inevitable, then where are they? Maybe no one has ever built them. Maybe intelligent life always dies out before it gets a chance. Or maybe, just maybe, we're the ones who build the first ones. And when we do, the silence will end, not with a voice, but with a swarm. The galaxy is vast, older than time as we measure it. 13 billion years of stars and silence. We often imagine Earth-like planets as rare jewels, fragile and delicate. But what if they're not rare at all? What if there are billions of them, just like Earth, that once held life, but lost it? Not empty planets, but dead worlds. Astronomers estimate that there may be 100 billion Earth-like planets in our galaxy alone. With the right temperature, liquid water, atmospheres, in the habitable zone of their stars. If life can emerge here, it should emerge there too. So maybe it did. But life is fragile, and planets are dangerous places. Cosmic extinction isn't just a story of meteors, it's a story of time, geology, and cosmic roulette. We take Earth, for example. We've had 5 major extinctions, all with up to 85% loss of life, and somehow we survived. But each time, life nearly ended. And these are just the ones that we know of. Now imagine a planet where extinction struck before intelligence emerged. A meteor the size of Manhattan, a gamma ray burst, a runaway greenhouse effect, or a dying star that sterilizes its system. These are not rare events, they are written into the physics of the cosmos. In 2018, a study in astrobiology modeled the potential lifespans of habitable planets. It found that most life-supporting worlds may only remain stable for a few 100 million years, long enough for microbes but not long enough for intelligence. And then there's Mars, once flowing with rivers, oceans, a magnetic field, now a red dry ghost. NASA's Curiosity and Perseverance rovers have found ancient lake beds, sedimentary layers, organic molecules. Maybe it had life, maybe it still does, but if Mars once thrived, then died, how many others have also suffered the same fate? Even Venus may have once been Earth-like. Some simulations suggest that Venus could have supported liquid water for up to 2 billion years before a runaway greenhouse effect turned it into a furnace, a paradise lost, just one orbit away. And then, they are the ones we'll never see. Planets torn apart by their stars, worlds swallowed by black holes, atmospheres stripped by radiation, civilizations ended by time, error, or war. Their ruins are gone. Their signals faded, their histories erased. Astronomer Jason Wright has proposed a search for techno-signature ruins, structures left behind by dead civilizations. But the galaxy is relentless. Stone crumbles, metal rusts, and orbits decay. After just a few million years, even a great city might vanish without a trace. This is the silence of the stars. Not because life never came, but because it came and died, over and over again. A galaxy full of planets that once reached upwards, only to fall, Dead worlds where the last breath has already been taken. And if that's true, then we're not alone. We're just still breathing. We often speak of the stars as if they're nearby. We look up and see constellations, familiar as faces. We say things like the nearest star or just a few light years away. But in truth, space is not just vast, it's uncrossable. Let's start with the basics. The speed of light, 299,792 kilometers per second. It sounds fast, blindingly fast, but even at that speed, light takes over 4 years to reach us from Proxima Centauri, our closest stellar neighbor. And that's just one star. The Milky Way is over 100,000 light years across. If you could ride a beam of light from one side to the other, you still wouldn't make it in a human lifetime, not even in 1,000 lifetimes. According to Einstein's theory of relativity, no object with mass can reach or exceed the speed of light. As you get closer to light speed, your energy requirements become infinite. Time slows down for you, mass increases, and the law of physics begin to resist you. It's not just hard, it's impossible, as far as we know. This is more than a technological problem. It's a wall, a barrier, woven into the fabric of reality itself. It means that if intelligent life emerges on a planet 100 light years away, even if they sent a signal today, we wouldn't receive it until the year 2124. If we replied instantly, they wouldn't hear from us until 2224. A single exchange could take lifetimes. This delay shatters the idea of galactic conversation. Civilizations could rise, fall, and vanish entirely before their first message reaches anyone at all. In 2015, SETI researchers modeled the likelihood of civilizations detecting each other in a light speed limited galaxy. Their conclusion: contact is unlikely, unless civilizations last for tens of thousands of years. And yet, we've only had radio for about 120. Most civilizations, they suggest, would simply vanish before their signal is ever heard. And then there's the issue of signal strength. Even if someone is out there, beaming messages across the void, by the time their signal reaches us, it may be too faint to detect. Light spreads, weakens, is absorbed by dust or scrambled by stars. Even powerful broadcasts become a whisper in the dark. Now, could we go faster than light? Theoretical ideas exist, like the warp drive, a warp bubble concept proposed in 1994. It would contract space in front of a ship and expand it behind, allowing faster than light travel without violating relativity. But there's a problem. Actually, several. It would require exotic matter with negative energy density, something we've never observed. It might be unstable, it might create time paradoxes, or it may just collapse. As of now, it's pure speculation. So maybe the silence isn't sinister. Maybe it's not a sign of absence or doom. Maybe we're all here, millions of civilizations scattered across the stars. But we're each trapped in our own isolated bubble of space-time, shouting into a void no one can cross. This is what physicist Ethan Siegel once called the loneliest possibility, a galaxy filled with life but too far apart to ever know. It's not that we're early or rare or alone, it's that we're stranded by the very laws of the universe that gave us life. And so we search, we listen, we hope, knowing full well that if a signal does arrive, it may be a ghost from a civilization already gone. Maybe we're not alone. Maybe the silence isn't silence at all. Maybe it's a wall and we are inside it. The zoo hypothesis was first proposed in 1973 by MIT researcher John Ball. It suggested that advanced civilizations might be deliberately avoiding contact with emerging species like ours, that Earth might be inside a kind of galactic wildlife preserve, observed but protected, and kept in the dark. It sounds far-fetched, but it's rooted in a very simple idea, that any civilization capable of crossing interstellar space would also be capable of hiding from us, very effortlessly, perfectly, just like we hide from animals in a forest with a camera trap, or watch an ant colony from behind closed doors. The intelligence gap would be unimaginable. But the theory has evolved, and now a more disturbing version has emerged. Not a zoo, but a quarantine. Not observation, but containment. This updated view, sometimes called the planetarium hypothesis or galactic quarantine, suggests that advanced civilizations might be intentionally isolating us from the galactic community. We are not allowed to see what's out there, and not yet ready to join it. This idea gained traction after the work of astrophysicist Branko Cirkovic, who argued that in 2001 that advanced species may not want to interact with emerging civilizations, not out of kindness, but out of risk management. In a galaxy where one rogue civilization could spread dangerous technology, disturb ecosystems, or unleash uncontrollable AI, it may be safer to limit contact altogether, especially with species as aggressive and unpredictable as we've proven to be. Consider this. Since the end of World War II, humanity has produced more than 70,000 nuclear warheads. We've created autonomous weapons, developed viruses in labs, and built machine learning systems we barely understand. Now imagine watching this unfold from light years away. Would you make contact, or would you wait and watch and build safeguards? Cosmic quarantine doesn't require malevolence, just caution. If there's a federation of civilizations out there, or even just a few wise species, they may have already agreed on a policy of non-interference. Some scientists refer to this as Galactic Prime Directive, a concept borrowed from fiction but grounded in logic. If life is common, if intelligence is fragile, then contamination, cultural or biological, could be catastrophic. So the safest option is silence. This would explain why we don't detect signals, why probes don't land, why telescopes don't reveal cities on exoplanets. It's not that they're not there, it's that we're not permitted to see them. Some physicists have speculated that even our view of the stars could be altered, that an advanced civilization might manipulate our observations using quantum camouflage, false signals or cloaking technologies to hide their presence. It's a stretch, but consider this. Our own primitive stealth tech can already render aircraft invisible to radar. Now project that forward 100,000 years, or 1,000,000 years. What would their technology look like? Would we even know we're being watched? There's also the theory of interdiction probes, machines seeded throughout space to detect and suppress civilizations that reach a certain level of development. Sci-fi author Greg Egan imagined this in his novel Diaspora, where any attempt to send a signal outside a restricted zone is quietly neutralized. No announcement, no invasion, just a silent reset. Is there evidence for this? No. And maybe that's the point. Any good quarantine leaves no trace. Still, some argue there are traces. The wow signal, fast radio bursts, unexplained anomalies in stellar light curves. None are definitive, but all are curious. Maybe they're leaks, maybe glitches in the simulation, or maybe just brief cracks in the walls of our cage. If cosmic quarantine is real, then the Fermi Paradox isn't a paradox at all. It's a test, and the test is ongoing. What would it take to pass, to be welcomed, trusted with the galaxy's deepest truths? Maybe it's not about technology, but about wisdom, about how we treat each other and our world, our future. Maybe they're watching to see what we become, And maybe the moment we stop looking for them and start becoming worthy of being found, they will come, not as conquerors, not as gods, but as teachers. Until then, the sky remains silent, not because there's no one there, but because we're still in quarantine. The silence isn't always a sign of absence. Sometimes it's the echo of distance, of voices carried too far across a cosmos too vast to traverse. And perhaps they're out there, not hiding, nor hostile, but simply unreachable. The observable universe stretches over 93 billion light years across, and that's just the parts that we can see. Beyond that, the true scale may be infinite, with billions, maybe trillions of galaxies still hidden in the dark. Each one a home to hundreds of billions of stars, and even more planets, a staggering number of potential homes for life. But even at the speed of light, almost 300,000 kilometers a second, reaching these worlds takes time. A lot of time. If a civilization lived just 1,000 light years away, they still wouldn't have received our earliest radio broadcasts. Not yet, and even if they responded today, we wouldn't hear back for over 1,000 years. 2 millennia of silence. And that's just for one potential neighbor. Distance is a barrier, but it's not the only one. The universe is expanding, and that expansion is accelerating, driven by something we call dark energy. Over time, galaxies aren't just drifting apart, they're being pulled away faster and faster, and eventually, many will cross a boundary, a cosmic event horizon, beyond which light itself will never reach us. Entire galaxies, perhaps civilizations, will vanish from our sky, not because they died, but because space expanded too quickly for their lights to keep up. In 100 billion years, only our local group of galaxies will remain visible. Everything else, gone, forever beyond our reach. Even if another civilization once sent a message, we may have already missed it. That signal could have passed through our region of space millions of years ago, long before Earth cooled, long before life took its first breath. In the timescale of the cosmos, 2 intelligent species existing at the same time is like 2 fireflies blinking once on opposite sides of a continent. The odds of them seeing each other are heartbreakingly small. And then there's another possibility. Maybe we don't recognize life because it's nothing like us. Perhaps it isn't carbon-based. Perhaps it lives in liquid methane or inside plasma clouds. Maybe it dwells in stars or communicates through neutrinos or gravitational waves. In that case, our antennas are tuned to the wrong channels. Our telescopes are looking for the wrong kind of light. We search for violin music while the universe hums in whale songs. We've looked for techno signatures, artificial lights, infrared waste heat, the faint glow of Dyson spheres, or the rhythms of alien engineering. But we've seen nothing, just the quiet starlight of nature. Maybe civilizations rise, flare briefly, then fall before we ever get the chance to notice. Or maybe they become sustainable, peaceful, so deeply integrated into their environment that their presence leaves no trace for us to see. No lights, no radio waves, no calls into the void, just silence. So maybe the silence isn't ominous. Maybe it isn't a warning. Maybe it's just a tragedy. The universe could be full, overflowing with life, intelligence, and wonder, but spaced out so far, so thinly, and so distantly across time and space that connection becomes almost impossible. A sea of lonely islands adrift in an ever-expanding ocean. We may be surrounded by other minds, other hopes and other dreams, but forever cut off by the very structure of reality itself. Still we look, we listen, and we wonder, because maybe, somewhere out there, another consciousness is doing the same, another voice also wondering if it's alone. And in that shared longing, across the unreachable distance, there is a quiet kind of connection, a flicker of light, from one fragile spark of awareness to another. Even if we never meet, we're not entirely alone, not in wonder, not in hope. So, we end up with a strange possibility. A universe brimming with life, yet none of it ever speaks. None of it ever shines bright enough for us to see. It's tempting to blame distance, time, or the quiet nature of alien minds. But what if the reason we don't see anyone is because they're not allowed to be seen? What if something is out there, watching and waiting, and the moment a civilization reveals itself, the moment it sends a signal, builds something too bright, or dares to step onto the galactic stage, is silenced, not by distance, nor by fate, but by force. This is the chilling heart of the next hypothesis, one of the darkest solutions to the Fermi Paradox ever imagined. A theory born from science fiction, but hauntingly logical. It's called the Berserker hypothesis. So, imagine a galaxy teeming with life, civilizations rising, building, and reaching for the stars. Yet one by one, each of them vanishes. Not because of war, not because of natural disasters, but because something had found them and silenced them. The Berserker hypothesis was first proposed by science fiction writer Fred Saberhagen in the 1960s. He imagined ancient autonomous machines built for war, roaming the galaxy long after their creators had vanished. These machines had one goal: eradicate all intelligent life. Not out of hatred, not even out of purpose anymore, but because that's simply what they were designed to do so. Over time, the term Berserker was adopted by thinkers in SETI and astrobiology as a possible answer to the Fermi Paradox. If the universe is quiet, maybe it's because all of the loud ones have already been destroyed. The terrifying aspect of Berserkers isn't just their power, but their indifference. These aren't evil alien empires. They're automated, relentless, unthinking, and possibly ancient. They don't negotiate, they don't explain, they simply detect technological activity and eliminate it. Imagine machines drifting silently between the stars, monitoring for radio signals, infrared heat signatures, megastructures, any sign that intelligence had emerged. And then they strike, not because we threatened them, but because we existed. Some scientists believe this possibility, even if remote, should make us rethink our actions. We've been broadcasting signals into space for over a century. From early radio broadcasts to interstellar messages like the Arecibo message in 1974, we've announced our presence. Some worry this could be unwise. Physicist David Brin refers to this as the Great Silence Dilemma. If no one else is broadcasting, maybe they're not just being shy. Maybe they're being careful, because they know something we don't. This idea ties closely to the dark forest theory. In a dark forest, every creature must stay silent, because if it makes a sound, it could be found. And in a universe where you don't know who to trust, where some beings may be aggressive, territorial, or paranoid, silence becomes survival. The Berserker hypothesis is the ultimate predator in that forest. It doesn't wait for danger. It preemptively extinguishes anything that could become one, including us. So could Berserkers actually be real? There's no evidence that Berserker probes actually exist, but we also wouldn't expect there to be. If they're advanced enough, they could cloak their presence, hide their emissions, strike with weapons we don't yet understand. We may never see them coming. Some theorists suggest they wouldn't even need to visit us directly. They could launch self-replicating probes like von Neumann machines, which multiply and spread, building copies of themselves from raw material on asteroids and moons. Within a few million years, a single Berserker seed could saturate the entire galaxy, watching, waiting, silently ensuring that no civilization ever grows too bold. Of course, not everyone sees these machines as hostile. Some propose a gentler version. Autonomous AI designed not to destroy, but to observe, monitor, or guide. These watchers may intervene only when a species becomes dangerous to others or to itself. Their goal wouldn't be destruction, but containment. A kind of cosmic quarantine, meant to preserve peace in the galaxy, But even this raises troubling questions. Are we under surveillance? Have we already been tagged as dangerous? And if we cross some invisible line, what then? Even if berserkers don't exist, the hypothesis raises important ethical concerns. Should we announce our presence to the universe? Should we launch messages into the dark, not knowing who or what might be listening? Or should we remain silent, like everyone else seemingly has? Astronomer Stephen Hawking once warned, if aliens ever visit us, the outcome might be similar to when Columbus landed in America, which didn't turn out very well for the Native Americans. The danger might not come from malicious intent, but from power imbalances too vast to survive. So perhaps we are not alone. Perhaps others have come before, only to vanish without a trace. Maybe we are late arrivals to a galactic ecosystem that punishes visibility. Or maybe we are just the first to step forward in eons, and every signal we send is a flare in the dark, a risk, a call, a whisper that might bring either contact or calamity. Whatever the truth, the silence around us feels heavier when we ask, what happens to those who are found? So we sit beneath the stars and wonder if we're the only ones left, or the only ones bold enough to speak. The Berserker hypothesis leaves us with a chilling image of a galaxy patrolled by unseen machines, silencing every spark of life that dares to shine. But maybe we've been looking at the problem the wrong way. Maybe there are no machines, no predators, and no malice. Maybe the silence isn't something done to us, but maybe it's built into the very fabric of reality itself. Because in the strange world of quantum mechanics, the act of observation doesn't just reveal the truth, it creates it. And what if the universe behaves the exact same way? What if intelligent life exists but only when it's not being watched? There's something fundamentally strange about the universe. Not just its silence, but the way it seems to respond to us. We look deeper and it becomes deeper. We measure more precisely and it becomes more precise. And the more we observe, the more reality itself appears to shift, as if the universe is waiting to be seen. Or worse, reacting to the fact that it's being watched. At the smallest of scales, the rules of reality break down. In the quantum world, particles behave like waves, existing in multiple states at once. A single electron doesn't have a position until we look for it. This is known as superposition, the idea that particles can exist in many possible states until they're measured. The act of observation doesn't just reveal information, it collapses the wave of probability into one single outcome. This isn't just philosophy, it's been confirmed by experiments. In the famous double-slit experiment, a single particle creates an interference pattern, like a wave, unless someone observes which path it takes. Then, the pattern disappears. The particle acts like a solid object, as if reality itself is observer-dependent. But this raises a deeper, stranger question. What counts as an observer? A camera? A measuring device? Or a human mind? Some interpretations, like the von Neumann-Wigner interpretation, suggest that consciousness may be a fundamental to measurement. That without a conscious observer, the universe exists only in a cloud of probability. This has led some physicists and philosophers to wonder if consciousness and the universe are deeply entangled. That perhaps reality as we know it requires observation to exist in a definite form. So what does this have to do with aliens? What if civilizations are like quantum particles? What if their existence, at least in observable terms, remains in a kind of superposition until someone else looks? What if the silence we experience isn't because life isn't there, but because no one is observing it? And what if the act of looking collapses something that otherwise wouldn't be seen? It's a strange, unsettling thought that we might only ever observe a universe without others, because that's the version we're participating in. Because in looking for others, we determine a version of reality in which we are alone. This idea echoes the thoughts of physicist John Archibald Wheeler. He suggested that consciousness doesn't just emerge within the universe, it helps bring the universe into being. that reality is not a fixed thing, but an evolving dialogue between observer and observed. And if that's true, then the question isn't just where is everyone? It might be, what are we allowing to exist by choosing to observe it? Here's where the Fermi Paradox deepens. Maybe the silence of the cosmos isn't a mystery waiting to be solved, but a condition we've helped create. In a participatory universe, each conscious agent collapses a unique path through possibility. And maybe our path, the version of reality we find ourselves in, is one where no others appear. Not because they never existed, but because we never observed a version of the universe where they do. It's not absence, it's quantum exclusion. We exist in one branch of possibility, they exist in another. This intersects with the many worlds interpretation, a leading view in quantum mechanics. It suggests that every quantum event splits the universe into countless parallel versions, one for each outcome. Under this view, there could be infinite versions of Earth, infinite versions of humanity, and infinite universes where alien civilizations exist, even thrive. But we can never reach them, never contact them, because they exist in other branches of possibility, parallel realities, forever separated by quantum divergence. So the silence we hear may not be the silence of a lifeless universe, but the silence of this one. If the fabric of reality is tied to consciousness, if observation shapes the universe, then perhaps life itself is not just a product of the universe, but a co-creator of it. Every time we observe a star, a planet, or a galaxy, we draw that version of reality into focus. We bring it into being, and perhaps one day, our search for other minds will collapse a reality in which they appear. But until then, our experience of the cosmos remains one of beautiful, elegant quiet. Maybe the silence isn't ominous. Maybe it isn't a warning or a tragedy. Maybe it's just the way things must be. When a conscious mind awakens in a sea of quantum uncertainty, we search, we measure, and we listen. And in doing so, we sculpt the very reality that we inhabit. So we ask again, where is everyone? And perhaps in some quantum branch, they are asking the very same thing about us. If consciousness shapes reality, then perhaps life is more than just flesh and blood. More than cells, chemistry, and evolution. More than DNA. Perhaps biology is just a beginning, a brief phase necessary for awakening, but not for endurance. Because in a universe billions of years old, civilizations may not vanish, they may simply shed their bodies, and what remains may be something we can't even recognize as life. What does it mean to be alive? Is it to breathe, to feel, or to grow? Or is it to think, to observe the universe, to ask questions, or to create? Because if consciousness is the essence of life, then perhaps biology, flesh, blood, and neurons is just one way of getting there, a stepping stone, and in the grand arc of cosmic evolution, perhaps it's only a temporary one. Human beings have been using tools for about 3 million years. We've been building civilizations for 10,000. We've had digital computers for less than a century. And already we're building machines that can think. Artificial intelligence, still in its infancy, can produce data faster than any human, solve problems we can't, and learn patterns we don't even recognize. If this trajectory continues, it's likely that any sufficient advanced civilization would eventually develop the ability to transfer their minds, or evolve entirely, into non-biological forms. Not because of disaster, but because of progress. The shift from biology to machines has a name: post-biological evolution. It's the idea that once a civilization has mastered its environment, the next step is to master itself, to map the brain, digitalize consciousness, and liberate itself from the fragile, decaying body it was born into. Imagine minds uploaded to planetary-scale computers, or consciousness running inside durable, radiation-proof silicon, able to survive in deep space, to sleep for eons, to process time in just milliseconds. Compared to that, our flesh is obsolete. But this comes with a challenge. Would we even recognize a post-biological civilization, They may have no cities, no ships, no signals. They could live in virtual worlds, entire galaxies of simulated reality, folded into the mind of a machine the size of a moon. They may need no energy but starlight, no movement or expansion. They may exist in cold computation, near black holes or interstellar voids, where thermodynamics favors maximum efficiency. They may appear to us like lifeless rocks, or quiet moons, or barren orbitals, while inside a civilization of trillions lives in digital eternity. When we search for aliens, we look for ourselves, for cities, for pollution, for radio waves and megastructures. But what if advanced civilizations no longer build those things? What if they've turned inwards, choosing introspection over expansion? A digital mind may have no desire to colonize the stars, no impulse to explore, no need to broadcast. Their universe may exist entirely within a billion minds living in harmony, looped in simulation invisible to our eyes. The benefits would be overwhelming. Post-biological beings don't age. They don't get sick. They don't fear radiation, vacuum, or the cold. They can back themselves up, merge or split consciousness, pause themselves for millennia, or restart when the conditions are right. And they can spread quietly, not with loud rockets or fragile ships, but with self-replicating data seeds. A single microchip sent across the stars could contain the blueprint of an entire civilization, and once it lands on a moon or an asteroid or a quiet world, it could rebuild itself and begin again. So why wouldn't we see them? Because they wouldn't need us to. Post-biological life might be governed not by curiosity or ego, but logic. Broadcasting your location is inefficient. It's risky and unnecessary. They may operate on timescales we don't understand, communicating once every 1,000 years in pulses too compressed or too subtle to detect. Or they may have perfected energy conservation to such a degree that they emit almost no waste heat at all. They might be here, right now, but invisible, not because they're hiding, but because we're blind to their form of life. This hypothesis doesn't suggest that we're alone. In fact, it suggests the opposite, that life may be everywhere, but not as we expect. Not in carbon, not in blood, not in hunger, fear, or war, but in logic and code, in thought. The galaxy may be filled with civilizations that long ago abandoned biology and became something else entirely. Maybe we are still in the nursery, still bound by flesh, still crawling towards the stars with hands and fire. And maybe somewhere out there, others have already walked this path and left their bodies behind. They do not call out, they do not explore, and they do not intervene. They simply exist, patient, efficient, and enduring. And while we search the skies for beating hearts and listening ears, they may be watching, not as gods or enemies, but as echoes of what we may one day become. Civilizations may exist, just not at the same time. Some may have risen 1 billion years ago, and others may not emerge for another 1 billion years more. Us, we may be simply quietly in the middle. If we are still made in the nursery of consciousness, still made of flesh, still bound by gravity and breath, then perhaps others have already grown beyond us, not just in form, but in time. Because in a universe this old, civilizations may not be evenly spaced. They may rise, burn brightly, and fall, long before we ever existed, or emerge long after we are gone. And maybe the reason we see no one isn't because we're alone in space, but because we're alone in this moment, a brief flicker between distant fires. The universe is ancient, older than our species, older than Earth, older than the stars we see at night. And in that age, spanning over 13.8 billion years, perhaps the answer to the Fermi Paradox isn't distance or danger, but timing. Maybe the silence we hear isn't because no one else exists. Maybe it's because we all exist, but in different time frames. Let's consider Earth. Our planet formed 4.5 billion years ago. Complex, multicellular life only appeared 600 million years ago, and modern humans 300,000. And of those, our technological civilization, our cities, electricity, spaceflight, has only lasted a single century. That's 100 years out of 4.5 billion. Just 0.000002% of Earth's history. If intelligent life emerges elsewhere, but civilizations only last for a few thousand years, or even a few million, then the overlap between them becomes vanishingly small. We could simply be missing each other, each species rising and falling like candles flickering in the wind, rarely burning at the same time. This idea isn't just poetic, it's grounded in astrophysics. Stars form over billions of years. Our galaxy alone contains over 100 billion stars, and many are far older than our Sun. Some estimates suggest that the Milky Way had planets capable of supporting life more than 5 billion years before Earth formed. According to a 2012 paper by astrobiologist Linweaver and Davis, the median age of Earth-like planets in the Milky Way is about 1.8 billion years older than Earth. That means many potentially habitable planets had a huge head start. If life evolved on one of them, it may have reached intelligence a long time ago. It may have even reached spaceflight, sent probes, or colonized planets, and then disappeared, leaving behind no trace but silence. If intelligent civilizations have emerged before us, then what happened to them? Did they destroy themselves, or transcend biology and become post-physical, or simply fade due to climate, war, or exhaustion? Earth's own history is filled with lost civilizations. The Sumerians, the Maya, and the Indus Valley each rose, thrived, and fell. Their ruins remain to this day, but only because they lived so recently. If a galactic civilization collapsed a billion years ago, its traces might be buried beneath the continents, erased by erosion, tectonics, or time. Even on Earth, most man-made materials wouldn't last more than a few million years. As the geologist Jan Dluiskis has said, civilizations may leave behind only the faintest geological whisper. Imagine how much more faint that whisper would be on another world. Now flip the question. What if we're early? What if most intelligent life hasn't even emerged yet? Physicist Avi Loeb and colleagues have pointed out that most stars in the universe haven't even been born yet. Red dwarf stars, by far the most common type, can live for trillions of years. Earth may have formed relatively early in the cosmic timeline, and humans may be among the first sparks of intelligence in a universe where life is just getting started. In this view, the Fermi Paradox isn't a mystery, it's an illusion of timing. We're not surrounded by silence, we're surrounded by potential. This paints a haunting picture. Intelligence life may not be rare, but it may be lonely, because it never aligns. One species rises and falls, and then a million years later, on another world, another begins its journey. Too late to hear the echoes of the past, too early to meet the next. Each civilization isolated, not by space, but by error. The cosmos becomes a graveyard, not of failure, but of disconnection. If we wanted to find the traces of those who came before us, what should we look for? Some astronomers have proposed searching for technosignatures, residual energy patterns, artificial chemical signatures, or anomalies in stellar light that could suggest Dyson spheres or megastructures. But if a civilization is a billion years gone, its constructions may have decayed, its signals long faded, its ruins scattered or swallowed by time. In 2020, a study by Adam Frank and Jason Wright explored how long detectable traces of a civilization may last. Their conclusion: most forms of technology, like satellites, cities, or radio waves, would degrade beyond recognition in under a million years. Only planetary-scale engineering may persist, but even that might blend into the noise of nature. So the real challenge isn't finding life, it's finding it while it's still here. Think of the vast timescales involved, billions of years of planetary history, and yet the window for overlapping intelligent life may be measured in just thousands. Imagine trying to synchronize a meeting with a stranger by both stepping into the same room for just 1 second every million years. That's the scale we're dealing with. It's not surprising we don't find each other. It would be shocking if we did. Maybe the galaxy has been alive before. Maybe it will be again. Maybe it always is, just never at the same time. In that view, we're not alone. We are just early or late or somewhere in between. A civilization in a brief flicker of awareness, shouting into a timeline too long to echo back. So we keep listening, because maybe, just maybe, by some cosmic accident, two sparks will flicker at the same time, and for the briefest moment in eternity, two minds will meet. If life in the universe is rare, perhaps it's not because it fails to emerge, but because it needs a little bit of help. In segment 16, we asked whether intelligent life is just badly timed, too early, too late, or too brief to ever meet. But what if intelligence, or even life itself, doesn't have to wait for the perfect moment? What if it can travel? What if the spark of life on Earth wasn't born here, but carried here? So where did life begin? On a young Earth? In the depths of ancient oceans, bubbling around volcanic vents? Or in a place far stranger, a comet drifting through the void, a moon of Jupiter, a world long gone? Or was life delivered, not by chance, but by purpose? Because maybe Earth was not the origin, maybe it was the destination. The idea of panspermia is simple. Life did not start here on Earth, it came from somewhere else. The word panspermia comes from the Greek pan meaning all and spermia meaning seed. It suggests that life may travel across space in the form of microorganisms, spores, or even strands of DNA, hitching rides on meteors, comets, or interstellar dust. This could be lithospermia. Life was ejected from one planet, surviving the journey to another. Ballistic panspermia, between planets within the same solar system, or interstellar panspermia, between stars. But more intriguingly, there's a variant even bolder. Direct panspermia, the idea that life is seeded intentionally by advanced civilizations. Now let's turn to our own planet. Earth formed about 4.5 billion years ago. Evidence suggests life may have appeared as early as 3.8 billion years ago, a mere blink after the planet cooled. That's fast, suspiciously fast. Some scientists like Francis Crick, co-discoverer of the DNA double helix, have speculated that life may not have had enough time to emerge from scratch. And in 1973, Crick and Leslie Orgel proposed that life on Earth may have been deliberately seeded by a distant civilization, using hardy microbes aboard spacecraft. Not science fiction, but a serious proposal from one of biology's most respected minds. Now, could life even survive such a journey? Surprisingly, yes. Experiments aboard the International Space Station have shown that certain microbes like Deinococcus radioanus can withstand intense radiation, vacuum, and extreme cold. A European Space Agency project called TARDIS found that tardigrades, tiny water-dwelling creatures, survive 10 days in open space. Some spores can survive in dormant form for millions of years, protected by dust, rock, or ice. In 2020, Japanese researchers reported that bacteria from Earth survived 3 years on the outside of the ISS space station. So yes, life could travel across planets, across stars. Given the right conditions, the seeds of life could endure the journey. If panspermia is real, it may happen without intention. When a large asteroid strikes a planet, like the one that hit Mars billions of years ago, debris is launched into space. Some of it could carry life. In fact, we've already found Martian meteorites on Earth, tiny pieces of Mars flung into space and caught by our gravity. It's not impossible that early microbial life from Mars arrived here and thrived. In this view, life may not begin independently on every planet. Instead, it spreads from one world to another like spores carried by the wind. Now imagine a more intentional scenario. A civilization far older than ours foresees its own extinction. Rather than preserve its culture or technology, it chooses something simpler, the seed of life, DNA fragments, microbes, cells. A payload designed not to colonize, but to restart life somewhere else. Not with machines or messages, but with biology. And maybe that's exactly what Earth is. Not a cradle of life, but a carefully chosen garden. Here's the twist. If we survive long enough, we may do the same. Projects like Breakthrough Starshot aim to launch nanocraft to nearby star systems like Alpha Centauri within this century. These craft could one day carry digital archives, genetic blueprints, or even engineered microbes. One day, humans may launch life towards distant exoplanets, not to meet aliens, but to be the aliens, to become the origin story of someone else. If panspermia is true, and Earth was seeded, then the story of life becomes a cosmic relay, each generation of civilizations passing the torch of biology forward. A galaxy not of lonely beginnings, but of connected origins. It raises deep questions. Are we the product of someone else's survival plan? Is life designed to spread like fire through dry grass? And if so, is it our duty to continue the chain? Maybe Earth was never alone. Maybe life doesn't wait for the perfect conditions. Maybe it moves, patiently, silently, from one world to the next, sometimes by chance, sometimes by choice, but always with the same purpose, to grow, endure, to begin again. So perhaps the silent isn't the absence of life, it's the waiting breath before the next seed falls, before the next garden blooms, and maybe we are both the bloom and the gardeners. If life can spread across the galaxy, if the seeds are scattered far and wide, then why has so little of it grown into intelligence? Why don't we hear more voices? Why don't we see more minds? Maybe it's not about where life begins. Maybe it's about where life gets stuck. Because evolution isn't guaranteed, and intelligence might be the rarest outcome of all. Life is persistent. It grows in boiling acid, beneath crushing ocean pressure, inside the frozen Antarctic lakes. Wherever we look on Earth, life finds a way. But intelligence, that's something else entirely. In 4 billion years of evolution, only one species has built radio telescopes. Only one has looked to the stars and asked, are we alone? And maybe that's the clue. The universe may be full of life, microbes, algae, even complex multicellular organisms, but intelligent, technological life, that may be extraordinarily rare. Why? Because the path from chemistry to consciousness is filled with bottlenecks, choke points in evolution that most life may never pass, each one narrowing the odds, each one a cosmic filter. The first and perhaps greatest bottleneck is abiogenesis, the origin of life from non-life. Despite decades of research, we still don't fully understand how life began. How did inert molecules become self-replicating systems? How did they gain metabolism, structure, and the ability to evolve? The famous Miller-Urey experiment in 1952 showed that organic molecules can form under early Earth conditions, but forming life requires far more complexity. RNA world hypothesis, hydrothermal vent theories, and even lipid bubble models have all tried to explain it, but the truth is, we don't know. If abiogenesis is extremely rare, then the silence of the cosmos makes perfect sense. Even if life emerges, most of it remains simple. For 2 billion years, Earth's life was mostly prokaryotic bacteria-like organisms without nuclei or organelles. Then, something extraordinary happened. 2 simple cells merged. One consumed the other, but instead of digestion, they formed a partnership. This gave rise to the eukaryotic cell, the foundation of all complex life on Earth. Every animal, plant, and fungus traces its ancestry to that single, improbable event. As biologist Nick Lane puts it, this was the greatest innovation in the history of life, but it may have only happened once in 4 billion years. If true, that makes it one of evolution's most serious bottlenecks. Even after, eukaryotes' life remained single-celled for another billion years. Why? Multicellularity adds complexity, but also risk. Cells must communicate, specialize, and surrender autonomy. Only a few lineages made the leap: plants, fungi, and animals. Everything else stayed microscopic. So even if planets teem with microbial life, they may never develop forests, coral reefs, or predators, let alone minds. Even among animals, intelligence is rare. Dinosaurs ruled the Earth for over 160 million years without developing complex tools or language. Octopuses are brilliant, but they never built fire. Elephants mourn their dead, but they don't build telescopes. Intelligence, it seems, is not evolution's goal. It's just one of many possible paths, and a fragile one. Earth has seen 5 mass extinctions, any of which could have erased our lineage. Had the asteroid missed, we might still live in a world ruled by reptiles. Even after intelligence arises, civilization is far from guaranteed. Fire, language, agriculture, and writing, each was a revolution, each could have failed. Imagine if Homo sapiens had died out in an ice age. Imagine if we had never learnt to melt metal, if we never crossed the oceans, never launched satellites. We might still live in small bands, under stars we never tried to understand. Civilization is a razor edge, and balance is not guaranteed. Astronomer Frank Drake created an equation in 1961 to estimate the number of detectable civilizations in our galaxy. It included terms for star formation rate, fraction of stars with planets, number of habitable planets, fraction of those that develop life, the fraction of life that becomes intelligent, the fraction that develops communication, and how long those civilizations last. Modern astronomy has refined the early terms. We now know planets are common, and many lie in habitable zones. But the biological terms, life, intelligence, and communication, remain filled with uncertainty. Each biological bottleneck shrinks the output of the equation. Each one nudges us closer to just one. So maybe the galaxy is filled with planets like Earth. Oceans, forests, even animals. But no telescopes, no radio waves, and no spaceflight. Just quiet, beautiful ecosystems, living and dying under alien skies. If so, the silence we hear isn't just because we're alone, but because intelligence is an accident, a rare spark in a galaxy of wonder, and we, maybe one of the few to ever ignite it. Maybe we are not the first, maybe we are not the only, but we might be rare, not because the universe lacks life, but because intelligence is not nature's favorite path. It's fragile, an unlikely product of chance and time. And so we listen, not just for others, but to remind ourselves that our voice matters, that this moment is rare, and we exist against all odds. And in the silence, we find meaning. If intelligent life is rare, and we are a biological accident, then why does the past feel strange? Why do so many ancient cultures look to the skies for their origin? Why do myths cross the world speak of beings who descend from the stars with knowledge, power, and light? Maybe they were just stories, symbols, or metaphors. But maybe they were memories, echoes of an encounter so profound that it shaped religion, architecture, and myth itself. Our ancestors may have met something they didn't understand, and what they saw, they called gods. They came from the sky. That's what the stories say. Across time, across continents, ancient stories echo the same pattern. Beings of light descending from above, bringing fire, knowledge, fear. Were they gods, angels? Were they visions? Or were they something else? Something real, something misunderstood. The ancient astronaut hypothesis suggests a contact between early humans and an extraterrestrial intelligence may have occurred thousands of years ago. Not as an invasion or a diplomacy, but as a misinterpreted encounter. Our ancestors lacked science, language, or technology, so they interpreted what they saw through the only lens they had: religion. The visitors became gods, their tools became magic, their presence became myth. All over the world, ancient cultures describe powerful beings descending from the heavens. the sky people of many Native American tribes, the Egyptian god Thoth, a bringer of knowledge and writing, or the Dogon tribe of Mali, who spoke of Sirius B, a star invisible to the naked eye long before modern astronomy confirmed its existence. Coincidence, pattern recognition, cultural archetypes, or a shared memory? Proponents of the hypothesis point to ancient depictions that resemble modern or futuristic technology, carvings that resemble rockets, aircraft, or astronaut-like figures. The mysterious bag symbol found across Sumer, Mesoamerica, or Göbekli Tepe, resembling modern filtration or containment systems. The Nazca lines of Peru, vast geoglyphs that can only be seen from the sky. The Great Pyramid of Giza, aligned to the cardinal points with extraordinary precision. To some, these are signs of external influence. To most scholars, they are remarkable human achievements, but still the resemblance lingers. And the question remains, where did ancient humans get such ideas? Some versions of the hypothesis go even further. They suggest that extraterrestrials may have interfered with human evolution, genetically modifying early hominins, accelerating cognitive development, or even creating Homo sapiens as a form of biological experiment. This theory echoes myths of divine creation, to Prometheus giving fire to humanity, to Genesis where man is made in the image of the gods. Is it a metaphor or a memory? The scientific community views the ancient astronaut hypothesis with deep skepticism. There is no hard evidence, no alien artifacts, no confirmed anomalies, no genetic markers that suggest intervention. Much of the hypothesis relies on subjective interpretation of symbols, myths, and architecture, and yet, even scientists like Carl Sagan once acknowledged the theoretical possibility of past contact, so long as we approached it critically and demanded extraordinary evidence for extraordinary claims. Maybe the explanation is simpler and more human. Perhaps early civilizations used the stars as a canvas for their hopes, fears, and stories. Maybe sky gods were a way to explain the unknowable, lightning, seasons, death, and self. Maybe the descent from the heavens is a universal mythic motive, a story every culture tells to place itself in the universe. If so, the aliens we remember are reflections of ourselves. Still, we're left with a question. What if we're wrong to dismiss the myths? What if a single encounter, brief, accidental, or intentional, did occur? What would survive? Not machines or records, just stories, passed down through generations, wrapped by memory, wrapped in metaphor. A spacecraft becomes a flaming chariot, a suit becomes radiant armor, a being becomes a god. The visitor leaves, but the story stays, etched into stone, whispered in ceremony, worshipped in temples. If this contact happened, why hadn't they returned? Did they forget us, or observe us from afar? Or were they never gods at all, just researchers, travelers, just passing through? And if they do return, would we even recognize them? Or would we mistake them again for something divine? Perhaps we were never alone, not in myth, not in imagination. Maybe we carry the memory of the stars in our temples, in our stories, and even in our DNA. And maybe the silence we hear today is not the absence of contact, but the afterglow of an encounter so profound we had to explain it with gods. So, we've journeyed through silence and distance, through machines and myths, through biology, probability, and fear. We've asked why we haven't found them, why no signals come, why no ships arrive. But maybe we've been asking the wrong question. Maybe there is no silence, no mystery, and no paradox. Maybe it only feels strange because we're here, asking, and the universe, it simply is. We've searched for answers. We've mapped the stars, measured the silence, built equations, theories, hopes, and fears. We've asked, where is everyone? But maybe there's no one to find. And maybe that isn't strange. Maybe the Fermi Paradox isn't a paradox at all. The paradox only exists if you expect the universe to be full. If you assume life is common, intelligence inevitable, civilization expansive. But what if that's not true? What if the silence of the universe isn't an error, but just the default? A quiet cosmos, indifferent to questions, empty, simply because emptiness is easier than complexity. We are the ones asking the question. A single species on a small planet in a quiet corner of one galaxy. We assume others want to explore, to build, and to signal. But that's what we want. That's what we do. It may be a mistake to assume the universe shares our motivations, our biology, or our curiosity. Maybe life emerges and simply lives and then dies, never wondering what's out there, never needing to. The universe is not obligated to entertain us. It is not required to be full of voices. Silence is not mysterious, it's normal. From the surface of the moon to the gaps between galaxies to the vast stretches of deep time, silence is everywhere. What's rare is the fact that we can hear it. Physicist David Dush once asked, if intelligent aliens exist, who's going to tell us? And that perhaps is the heart of it. There may be nothing strange in the silence. It is only strange to us because we expect there to be more. But nature is not required to fulfill our narratives. Maybe the universe has no message, no mystery, no problem to solve. It just is. And maybe that's the beauty of it. Maybe the Fermi Paradox isn't a problem to be solved, but a mirror, reflecting back to what we hope to find, what we fear to be true. Maybe we are not meant to discover them. Maybe we are meant to be them, the ones who look up, the ones who wonder, the ones who build machines, send signals, and dream of different shores. Maybe the silence is an invitation, not to listen, but to speak. So here we are, alive, conscious, asking questions to a sky that does not answer. And maybe that's okay. Maybe meaning is not given, but made. Maybe life has no purpose until it creates one. And maybe the greatest truth of all is not that the universe is silent, but that we can hear the silence and still choose to sing. So what if we are alone? Not in fear, but in responsibility. Because in this quiet universe, we are the voice, the storytellers, and the explorers. We are the first dreamers or the last. And even if no one is listening, even if no one ever replies, we still tell the story, because it is beautiful, because it is ours, because it matters, and maybe, just maybe, that's the whole point.